Hi everyone, my name is Hannah Gumble and I'm currently a PhD student at the Bartlett Centre for Advanced Spatial Analysis, and I'm going to be presenting my early research on creating a raster agent-based modelling environment from crowdsourced geographic information. So just to give a brief overview of sort of the presentation, I'm going to begin with some context, talk briefly about the OpenStreetMap data used and the methodology and the workflow that was done in ArcGIS, and then the results which were gained from the Python Mesa agent-based modelling framework, and then draw some conclusions. So the context of this study was really to examine the viability of processing OpenStreetMap data into a fine-grained agent-based modelling simulation. So we really wanted to know if it was suitable for a street-level simulation. So just to introduce all the agent-based models, they model at individual behaviours. So it's really a bottom-up approach to understanding a system. And agents exist, interact, react, and can adapt their behaviour based on the environments that they're in. So the environments can be quite a core process of a model. And there's several forms that they can take. So they can be hypothetical or database. And when they're database, the use of geographic data is increasing, but there's little focus on its quality in agent-based modelling simulations and the effect that that could have. So because of that, there's no recommended approach or guidelines as such. And on the right-hand side, you have just 3 examples of some geographic data that's been used. So there's 2 which show road networks, and then 1 raster-based elevation agent-based model. So just to talk about sort of crowdsourced geographic information, like there's really an evolution from national mapping agencies doing large-scale updates to a more crowdsourced patchwork approach with multiple contributors. So in some areas, data availability and the update rate could be really significant and maybe rich enough to support fine-grained simulation environments. However, this might not be the case for everywhere. So the aims of this research are really to create a workflow in order to take the OpenStreetMap data into a raster dataset, test the impact on model initialization when it's put into an agent-based model, and highlight some of the limitations of using OpenStreetMap as the data input. So the data itself. So to the left, you have the OpenStreetMap data that you would see on the website when you log on, and you can export that using the built-in tool. And we extracted this for the area of the City of London. And then on the right, you have the raw data that we visualized in ArcGIS. So the data is mainly in the form of polylines. And there's a distinction between building purposes. So you have leisure, tourism, and things like that. And the rows are represented by a single line. And there is some mapping of curves, which can be seen in the green lines. So our methodology contained 4 stages. So the first one was sort of like data preparation, followed by processing the buildings, then looking at the highway processing, and then creating the raster. And then once this raster data was created, it was fed into the Mesa agent-based modelling environment. So just to highlight one key step that was sort of quite a stumbling block was converting the single lines for highways into a space that an agent can occupy within a model. So the data from OpenStreetMap classifies road types based on whether like highways, local roads, and a lot of these are open to a lot of interpretation based on the data contributor. And there are no attributes such as road widths or anything like that. So we really had to think about, okay, we have a line, how can we create the representation of the actual road? So to do this, we use curb-to-curb data that we gained from OpenStreetMap. And for each street type, we measured one side of the curb to the other side of the curb to create an average that we used as a proxy. But this was also quite a limited way of doing it because curve data wasn't always available. So our GIS output. So on the left-hand side, you have the shapefile that we fed in to create the raster file. So from that, you can see that the building polygons have emerged into more blocks because we didn't necessarily need the detail within that. And then for the road types, you have them classified by type and based on permitted travel direction. So whether they're one way or anything like that. And then on the left-hand side, you have one of the raster outputs at the top. And then below that, you have a comparison of sort of 3 raster areas with different cell sizes. And one of the biggest things is a lot of agent-based models are really visual. And so when you look at where the raster has a cell size of 1, the roads appear a lot less linear than if you had a greater level of detail. And so this is quite important, as it would change the way in which the agents are visualized within the model and create sort of like a less realistic agent movement. So initially, we planned to run on the MESA visualization server. However, there was sort of a bug and a limitation within the program, and it couldn't visualize the level of detail we wanted within the visualization server. So we sort of took a step back and said, okay, let's run it a different way and look at the model load time. So when you run MESA and call your model, how long does it take to load up before it starts running? So that is what's in the graph on the left-hand side. So you can see that with decreased raster cell size, so the greater level of detail that you have, the highest time in seconds that it takes in order to load up. And this is quite important because the difference in load up time could also represent a possible difference you would have based on agent steps within the model, because there's just that greater level of detail that you need to go through. So then I kind of said, okay, so we've looked at in MESA, we have the visualization server issues. Let's go to another tool such as NetLogo and visualize it in there and see what happens. So for this, I put in cell size 1 because it's the most manageable data set. And it was very similar to MESA, in which it took less than 1 second of load time in order to load up before then you could run the model. But then taking that forward into the raster grids with the greatest level of granulation, again, there was the problem of actually NetLogo trying to handle that amount of data. And it also shows a limitation based on processing power and also the capabilities of the servers, tools, and like software and hardware that you're going to use to run the model. So this was a key consideration that I hadn't really thought of when I initially sort of started the project.
3 minutes.
So to draw some conclusions, so for this research, a workflow was presented, but it's a very initial workflow and is one possible option in which it can be applied. So it's at the very early stages. So to sort of move this research forward, the next step is to sort of examine other line rasterization procedures. So look at the different ways and say, okay, how can we turn these lines into streets more effectively? And what is the comparison between that? You then, we saw that there was a very strong relationship between raster detail and model initiation time. So that was a clear pattern to be seen. And as I mentioned before, that could be actually really critical when you are looking at whole simulation runtimes. There was a lot of spatial inconsistencies in the mapped features. So the attribute detail that was missing. So we had our road drawn, and for most of them we had a road type classification. But as I said, we didn't have things like road widths, cycle lanes, and what side of the road they was on. And then we also had the missing curve data. So that was a key limitation of the street level simulation. So some of the key limitations of the study as a whole, sort of moving away from just the data limitations, is that at the moment we've only examined one area. And as it was noted in sort of the context, there's a very big spatial variation in the level of detail in an OpenStreetMap sort of system because of the crowdsourced approach. And then we also, this is, as I said, it's just one methodology. And we didn't have the potential to look at the effect on full simulation times and exported model results. Then also this was primarily MESA focused. So we set out with the intention of using the Python framework for the agent-based model, but there are lots of different packages and they might respond differently. So if you went to something like Mason, it could respond very differently. So sort of future studies should compare with other locations, draw those parallels and those differences, analyze the effect on the actual simulation times and then the outputs, which would also really strengthen this research, and then test the differences between the agent-based modelling frameworks.
I have a few questions. I'll start with quite a practical question, Anna. So I do a bit of agent-based modelling myself, and I've been quite interested in Mesa. I've not had a go yet. It has the potential, I guess, to be quite a big thing to have a decent integrated Python-based system. In your view, is Mesa heading towards being a success, having used a few systems now?
I think the starting point of Mesa is really strong. So when you go to actually learn into it, they've got quite a few tutorials, and there are sort of packages out there which you can apply and sort of built-in functions. But one of the things that I would say is that it's still quite an initial way of doing agent-based modeling. So you have the basis that they've set up and the example models and the functions they've used for them, which are available to call from sort of the Mesa model, the server for visualization. But actually then modeling something that necessarily they haven't modeled before could be a lot more trickier than if you used a more established package. Just because if you want to use a certain function, you have to like create it by itself. And also there's a lot of, it's all on GitHub Mesa, which is really good because then you can contribute and also highlight any problems, and they are very responsive and sort of coming back to you on that. But in terms of moving it forward, it's kind of hindered until people undertake very different simulations that sort of push the boundaries of using it.
Great, thank you very much. It's very insightful. We've got a question from Labib in the Q&A box. Can you clarify a little bit more why the road attributes are needed and how you convert multiple attributes to raster grids, please?
Yeah, so for the road attributes, when you get that raw data, it's given to you as a line, and that's what you can see and visualize. But when someone puts a road into OpenStreetMap, it will prompt them for other variables. So something like surface quality, the classification of the roads, whether it's more of a local road, a highway road, is it one way? Can you have cyclists cycle down the road is another one. But one of the things that was quite important to this work was that it didn't say, okay, what is the width of the road or the average carriageway width? And therefore, when you're trying to convert that sort of single line into a sort of space that an agent can occupy visually, you're kind of quite hindered in that way. So that was one of the reasons why the level of detail that is provided by the person contributing is quite important, because people have a perception of what they view as the important details when they add a feature. And therefore so some people are quite inconsistent. And so some contributors just draw the spatial feature, and then others can go and add the details. So it's sort of understanding that limitation of where that detail is, where it isn't, and then how that affects what you can do with the polyline that you have and the actual space that you need to model.
Lovely, thank you very much. Excellent answer. Right, we've got time for one, maybe two more quick questions. We've got one from Cecile, which says, thank you. And are you developing a Python package for this? And I guess more generally, are you going to open source your work here?
Yeah, definitely. So in my actual PhD, I'm building a model to look at micromobility and modeling a new form of transportation. So as that develops, that will go onto GitHub and also be used. And as I develop functions, my plan is to submit them to the GitHub creators for them to go through and hopefully add them to sort of strengthen the environment, because I really believe in sort of like that open sharing of code and data, and that's how sort of things progress forward.
Fantastic, thank you very much. With nothing else in the box, but I've got a stack of questions, so I'm going to steal the last one, if I may. So could you just say a little bit more about the motivation for using the kind of VGI OSM as opposed to the master map, for example, which does have those attributes inside it? What's the big driver in your case for using that open data?
I think for me personally, I'm sort of a big believer in the potential of crowdsourced data. So that's sort of one of the main motivations for me personally. And the other thing, as I said, you kind of have national map agencies which give sort of wide scale, like set fixed time updates. But when you have a dramatic change, crowdsourced data can be a lot more richer. So when you look at things like coronavirus and obviously changes in street use, so in London you've had streets which have been fully pedestrianised, and that is like a really big impact when you're looking at modern mobility. But actually in a larger scale data set, they might still have a car can go down there and things like that. So it's really thinking about the study area that I had and thinking about, okay, when I want this level of detail, what would be most applicable? And especially because I'm looking at particularly the spaces in between the buildings and actual pavement use and pedestrians. So OpenStreetMap has things that put in like bus stops, cycle racks, and those smaller features that really affect urban movement that aren't necessarily captured in the large scale data sets.
Lovely. That's great. Thank you very much, Hannah. That was a fantastic presentation and some excellent answers.